Hello, everyone. I'm Steve Brown, Associate Director of the AI Institute for Next Generation Food Systems. This panel is titled Using AI to Understand and Demystify the Complexity of Food Systems. The topics today will generally surround envisioning what next generation food systems could look like and how AI can help develop new solutions to address long-standing, difficult food system challenges related to crop and food production, supply chains, nutrition, public health, and impacts on and from climate change and more. Our panelists are Dr. Elias Tagapoulos, Director of the AI Institute for Next Generation Food Systems and Professor of Computer Science and the Genome Center at the University of California, Davis. Also, Dr. Danielle LeMay, Research Molecular Biologist with the USDA ARS Western Human Nutrition Research Center and Associate Adjunct Professor of Nutrition at UC Davis. And our third panelist is Dr. Mason Earls, Assistant Professor of Viticulture and Enology and Biological and Agricultural Engineering at UC Davis. With that, we'll pass it along to Dr. Tagapoulos.
Thank you, Steve. Hi, everyone. I'm Elias Tagapoulos, Director of AIFS, or AFIS, the AI Institute for Next Generation Food Systems, which is what I will introduce. I will discuss about our goals, initiatives, and organization. So let's start with a brief history of the US food system. We are at the precipice of a major disruption. We started at food 1.0 with industrialization, globalization. Food 2.0 would be with agrochemicals, nutrients, and monocultures in the past century. And now with precision agriculture, there are so many things that they are changing and are constantly changing, with many of the enablers being sensors, devices, AI, data and analytics, consumer demand, global food safety markets. Of course, we have a lot of barriers. It's gap between tech and ag sector. A lot of the technologies, they are side products. They are not made for the food system, and that creates a feed gap. Data, software, and hardware infrastructure that doesn't reach everyone, innovation gap, access to markets, education and outreach that always needs to be there to close this gap. In terms of the fact sheet, and this is a slide that I presented also 2 days ago, we split it into three parts: workforce, environment, and health. So in terms of the workforce, farmers account 1% of the US population, a staggering difference from a few years ago or a few decades ago, where it was a 2-digit number. About 1/2 of the higher agricultural labor force lacks authorization to work in the US and creates, of course, a lot of systemic risk. 6% of production comes from 5% of large-scale family farms. So this is like a big discrepancy between large-scale and small-scale farms. In terms of the environment, we have many challenges. Pesticide and herbicide use has increased 10 to 20% over the past 5 years. Agriculture is responsible for 9.3% of the total US greenhouse gas, or around 10% of the US greenhouse gas emissions. And about 1/3 of the food supply is lost, which is such a waste. In terms of health, we have 41% of the US adults over 20%, and over 20% of the 12 to 19-year-olds that are obese. And at the same time, we have 1 in 8 families in America being hungry, which again is it's an oxymoron. For that, we created AIFS, which is the AI Institute for Next Generation Food System, and its mission is to develop and leverage transformative AI for the ethical production and distribution of safe, sustainable, nutritious food with fewer resources. AIFS is a collaboration, a partnership among 6 institutions, UC Davis, UC Berkeley, Cornell, Illinois, USDA, and ANR, which is Agriculture and Natural Resources of University of California. The partner organizations are Research One, top-tier universities, land-grant agricultural schools. They are having complementary in terms of AI and computational science, as well as, of course, nutrition and agriculture and food science. And with a lot of diversity among the researchers and the staff in the institute and the shared vision. Now, going regarding the way we are approaching the system, again, how we see the food system, it's more of a holistic approach. And next slide, please. Yeah. So it's a holistic approach that we see the food system as a whole, and we are breaking it down into 4 verticals: molecular breeding, agriculture production, food distribution and processing, and nutrition. And we're focusing on plants. And we're having 2 overarching themes. One will be the people behind it, the workforce and stakeholders, and also the technology. So AI and technology as an enabler. And we have structured our clusters, our research cluster around this theme. So artificial intelligence, AI, is more of the connective tissue, the glue that puts all of them together. And we see that as the enabler, that it creates a platform where the applications, the solutions come together. So it's not just predictors or small-scale modules that we have within a micro project, but it's something that's much, much more of a bigger scope. So, and one last but not least here is the ethics and socioeconomics cluster, which again, you cannot have a food institute, even an AI one, without being concerned about ethics, not only because of the ethics of the food, but the ethics of AI, which can be very biased and can be very difficult to interpret and can create inequalities without even us knowing. In terms of IFS participants, we have more than 50 professors and researchers, and we have collaborations of 5 staffers, and the associate professor is, associate director here is Steve Brown, that you already met. And we have many collaborations with different other institutes, including CITRIS, the Vine, and the IIFS, Innovation Institute of Food and Health, or as well as the Institute for Food and Agricultural Literacy. In terms of engagement, COVID derailed a little bit our plans, but we have a lot of great programs that we are going forward: speaker series, career exploration fellowships, industry and public engagement, curricular enrichment, training and workshops, conference and symposia. Of course, conferences are mostly in Zoom. We still haven't had a big in-person conference workshop, but we are working on that. In terms of projects, the first year we have funded 16 projects. So we were bed hedging and exploring the space until we're focusing on what will be the major thrusts. So these projects, they come into different thematic areas that they are following closely our research clusters. Core AI, projects around data efficiency, reinforcement learning, food safety assessment with statistical learning, molecular breeding with accelerated multi-trait breeding, different trait prediction, food processing distribution, looking at leakage, spoilage, digital twins, machine learning for pathogen and prediction, and fresh production sanitation. In terms of agricultural production, we have yield sensing, so both yield and quality related projects with autonomous ground and aerial delivery, stress sensing, resilient food optimization, as well as digital twin machine learning for robotic production. Nutrition has 2 projects for this year, predicting health effects and prediction of glycan content of different foods. Okay, and so of course, the ethics and socioeconomics, it has 1 project that is overarching. It looks at the ethics at all different areas that they used to work on. In terms of a case study, so we're going to look at 2 different projects. In the nutrition AI, our vision is being able to go start from foods, ingredients, and diets, and end up with health effects. And being able to predict and translate to practice. So you're starting with analytical data collection, where you see here we have different omics as well as vitamins and minerals. We continue with processing of this information, integration, and of course, it's not just the data, but also the metadata that need to be cleaned up. And you have to do a lot of pre-processing so they can be used down by AI and different machine learning methods. We can formulate hypotheses. We can create models on top, both mechanistic and statistical. And all this knowledge can be represented in a huge knowledge-based graph. And then we can use different knowledge graph completion algorithms like entity and missing link prediction to be able to find all these new associations and then test them, validate them in the lab, and translate to practice. By doing that, we believe that we can bring global and integrated data systems, standardized and metrics for all, and then accelerating discovery in nutrition. This is another project that you see here, agricultural production, where we are having it's multiple projects that are connected together. So you can start from, it's a farm to fork, but we're starting with farms, olives, grapes, almond, and strawberry, digital twins, and AI data generation with 3D simulation. We continue with data inputs and multimodal data streams that include climate, weather, soil, environment, and management. Then different models coming from our AI cluster with that they are ag optimized and ag based. And then we are moving on prediction and recommendation of yield, ripeness, forecasting, etc. And with that, I'd like to thank you and give them back to Steve.
All right, thank you, Elis. We'll now move on to Dr. Danielle Lemay.
Hi, everyone. I can't see you, but I'll just assume you're all there, and I look forward to your questions that come through the chat and at the panel. So I'm happy to be with you today to talk about how we're starting to use AI in nutrition and plan to in the future. So next slide, please. So what do you plan to eat tonight? That's my kids' favorite question. They come running in asking me what we're having for dinner every single night. And if you're the food provider for the family, I empathize with you. So all of us eat, but what should we be eating? Sometimes that's less clear. There's a lot of information available that's not necessarily backed by scientific evidence. So one of the goals of the Human Nutrition Program is to develop the scientific evidence for what we should be eating. So there's emerging evidence that how we respond to our diets is highly individual. You and I could both have a snack of carrots and hummus, and I would have a different response to that snack than you would. But we are only just beginning to understand some of those aspects of the individual response to diet. Next slide, please. So in effort to better understand our individual responses, the USDA Nutritional Phenotyping study was initiated. This is a cross-sectional observational trial of more than 350 healthy adults. So what I mean by that is we're looking at all kinds of things about healthy adults at a single time point. These adults were, since all of you are, or many of you are Yolo County residents, I just want to say, like, these people were recruited from Davis, Woodland, Sacramento, like in our region. So we collected all kinds of information from them, including dietary information that was self-reported in the form of like food frequency questionnaires and 24-hour recalls, asking people what have they consumed in the past 24 hours. So next slide, please. The people in this cohort were challenged with many different ways. One of which was a test meal where we gave people this really high-fat shake and then took their blood throughout the day to understand how they responded to that shake. They were also put through, fitness tests. Like, as I said, their metabolic response was also measured. That's that upper right-hand corner, somebody on a metabolic cart. The lower left-hand corner is somebody on a DEXA tables. So that's where we're measuring their bone mineral density and their body composition. Then that lower right-hand corner is somebody having an endopat test done where we're measuring vasodilation. Next slide, please. But the point that I really want to bring home is that this is a lot of information. So not even including the so-called big data for each participant. We have around 7,000 data points for each participant, all in this REDCap database. And so what do we do with all that data? Well, at least one answer to that question is machine learning. Next slide, please. So I should probably explain what is machine learning. So first, artificial intelligence is really this broad class of techniques that mimic human intelligence. And then machine learning is a subset of AI that extracts information from data to predict or classify any new data coming in. And then deep learning is a subset of machine learning that involves feeding data to software that's like inspired by our brains to perform complex tasks. Next slide, please. So I'm sure you've all seen some kind of science fiction movie or something where, you know, the machines take over. So I just want to explain what machine learning can do and cannot do. Like, we can use machine learning to forecast or make predictions, to memorize, to reproduce, to choose the best item. Machine learning is not going to create something totally new or get smart really fast or go beyond their task, and certainly not kill all the humans. Next slide, please. So you might be asking, well, you know, what kinds of things would we use machine learning for? You'd want to use machine learning if you're making classifications, like predicting a category. When you want to regress or predict a number, if you want to cluster data, reduce complexity, and you have a large number of independent variables. And you have enough data to learn from, really a lot of data. I also want to say that historically, we've been using machine learning to make predictions, but in the biological sciences, like in the nutrition scientists, we're increasingly using it for explanation. So what do I mean by explanation? I mean, really determining which of those variables matter and like by what magnitude and direction. So next slide, please. So some examples of how we use AI in my lab are we're now processing images to try to predict the labels from food ingredients. And admittedly, we don't have a whole lot of experience in that label, so in that area. So that's one of the wonderful things about an AI research institute, is having other colleagues that we can reach out to. So Mason Earls, who you'll hear from in the next talk, is actually one of those colleagues we've reached out to for the computer vision work. We also use machine learning for simple like classification and regression problems to figure out, you know, how particular dietary intake predicts particular health outcomes. And you know, if you're a scientist or even many non-scientists also use regression in their work, and as just part of regular statistics. And you might say, well, why do I even need machine learning to do that? Next slide, please. And you'd be right. Scary equations aside, really when you are doing a regression, that's true. If you only have a few variables that predict the outcome, you don't need machine learning. But in really complex problems, we have many variables. In traditional multiple linear regression, it's just not practical to have that many variables in your regression. But with machine learning regressors, the number of variables can be really quite high, and the algorithms do their thing to eliminate features or to shrink coefficients. So you really can analyze much larger data sets. Next slide, please. So there are two main ways that AI will help us in nutrition research, and probably more than these, but these are the two that I think about and One is tracking what individuals eat, and the second is predicting impact on health. So first we'll talk about tracking what individuals eat. Next slide, please. So I'd first like to explain, very briefly, like how we conduct human nutrition studies. There's a lot of different ways to conduct human nutrition studies, but they all boil down to just two main methods. And that's observational, where we're just capturing what people eat on their own and we're measuring outcomes. That's fairly cheap, so we can include lots and lots of people in those trials. Then there's intervention trials, and that's where we're directly controlling everything that we're feeding people and measuring the outcomes. And that's very, very expensive. So we can't include so many individuals in those trials. So as you might imagine, we'd like to be able to do more observational trials because we can include so many people, but the data is not quite good enough, and I'll explain what I mean by that. So next slide, please. The best way of explanation is probably by a particular example. So say you had these 6 people before you, all of different body mass index. If you ask them, please report your dietary intake and your physical activity levels, could you predict, based on their diet and physical activity levels, which of these categories the people would fall into? That seems like a pretty reasonable task. Next slide, please. But it turns out that this was actually done in a study of over 90,000 participants using food frequency questionnaires. And on the I don't know that my cursor works here, but on the left-hand side, you see that's the actual class of underweight or normal weight, overweight, or obese. And across the top is the predicted class. And you can see it was actually really difficult to predict weight class, even after half of the data was thrown out for quality control issues. All of the underweight people were incorrectly predicted as normal weight. That's actually worse than chance. Nearly half of the normal weight people were predicted as being overweight or obese, and more than half of the obese people were predicted as being normal or overweight. And so I'm not picking on the authors here or anything. I think it was a great study and they didn't do anything wrong. It's just that the something wrong here is not the algorithm. It's really that the underlying data is not very good. It's well known that when people report on a food frequency questionnaire, that they're really underestimating their food intake. Next slide, please. So self-reported. So as I mentioned, the problem here is really that the self-reported dietary intake data is poor. So what might we possibly be able to do about that? Well, we know one of the major problems with self-reported dietary intake is that people cannot remember what they ate and cannot really accurately report what it was or how much. Next slide, please. So what if we could make food reporting a lot less obtrusive? So imagine a future in which we can take pictures, the AI algorithms correctly predict those labels, and the participants confirm or correct them in real time. There are actually apps on the market today that are attempting to do this, and we are getting closer over time, but they're really not validated yet for research purposes. But as the algorithms and the databases get better, this will become more viable. Next slide, please. So the other aspect I want to talk about is using AI to predict impact on health. Next slide, please. So even really simple machine learning models are informative in nutrition research. We recently used machine learning to classify stool samples as hard, normal, or soft. Now, why would we need to do this? I mean, surely we don't care about people's poop shapes. No, in this case, we really cared about the explanation. We wanted to know what are their dietary features that correspond to normal or abnormal stool. And then once the stool form was classified, we were able to use another algorithm to iteratively test each of the input features and to determine the magnitude and direction of those features. So, and then for each class in the model, we were able to determine the impact on the model output. So we created a lot of graphs that look like that graph on the right there, but we took the liberty of simplifying them. Next slide, please, to something that's a little easier to look at. So for like each stool shape here, an up arrow is indicating there's an increase in magnitude of that factor increases the probability of that stool type. And a down arrow means that a decrease in magnitude of that factor increases the probability of that stool type. The traditionally favorable dietary factors you can see there are in green, unfavorable ones in orange and red. Stress hormones actually seem to really contribute, and those are shown in purple, and remaining physiological factors are shown in black. So for example, the probability of normal stool is increased with increased consumption of vegetables. No surprise there, although there were some other surprises for us. But the take-home message really that I want to get across is that it's not like any one component predicts stool consistency. It's actually a constellation of components, each with small effect sizes, and that's why machine learning is really helpful. So next slide, please. In another project on food and bone health, we built regressors for bone mineral density, and we found that several types we used several types of machine learning models, and even though sex and menopause status and BMI and height were such strong predictors of BMI as we expected, we were still able to find some dietary predictors that predict BMD as well. Next slide, please. One of the largest and most successful machine learning examples in nutrition was this massive study in which 800 people were given over 46,000 challenge meals. It's really a lot of meals to prepare. Their blood work and microbiomes and genotypes and questionnaires and physiology were all then used to train a machine learning model. Excuse me. And then an independent cohort was used to validate that model. On the right-hand side, there's these four plots. I don't know if my cursor works, but there are these four plots. Oops. Back, okay. On the right-hand side in the graph B, that's upper left, you can see the carbohydrate content of the meal alone is somewhat predictive. The caloric response a little less predictive, but what was really a much better prediction was all the person-specific characters together, and then the same was shown with the validation cohort. So this really demonstrates that there's some personalized response to a meal. Okay, next slide, please. So within nutrition, we're really attempting, as Ilias also mentioned, we have this grand challenge really to assess diet in real time and to convert that dietary intake into molecular structures and to predict the impact of those structures on consumer health and well-being. And this is really a massive goal, and we sort of broke this down into one slice that our team has some expertise in, and that's looking at glycan structure. So glycans are carbohydrates, it's just fancy name for carbohydrates. And the reason we care about them is that, well, I, in the past, have studied milk biology. And one of the most abundant components in human breast milk is not even there to feed your infant. It is there to feed the infant's gut microbes. So that tells us that the structures, these carbohydrate structures in diet are really important, even though they are not, they don't appear in our food composition databases. So that's a major research gap that we plan to tackle. So one of the very first things is being able to properly assess people's diets. So our first goal is real-time dietary assessment. And the second goal is being able to, convert like food images that we're collecting from participants into what are these glycan structures. And then finally, the third goal of predicting effects of those glycan structures on microbiome health. Let's see, next slide, please. So our long-term goal is to obtain precise and personalized nutrition recommendations for consumer. So today, USDA MyPlate can only personalize on like age, sex, height, weight, and physical activity level. And it gives really generic food group suggestions, but not specific foods. So in the future, we're expecting that personalized nutrition should be extended to your health status, your genotype, your microbiome, whatever features we identify using AI. And the precision will improve from generic food groups to specific foods. So not just eat more fruits and vegetables, but hey, you need some more chickpeas, and you over there, you need more pears. Many challenges remain, but with each passing year, we're getting a little closer to this holy grail. So next slide, please. I just briefly like to thank the USDA Nutritional Phenotyping team, because that is a really massive study that they pulled off, and many UC Davis collaborators. Of course, my lab, this is pre-pandemic lab shot. We've grown since then. And extra thanks to our postdoc computational biologist, Dr. Elizabeth Chin, who's been doing a lot of the machine learning in my lab. And now we get to hear from Mason Earl. So next slide, please.
Hello, everybody. First off, thank you for having me and us here at this very important summit on food for fairness. So I'm going to talk a bit about equitable, sustainable AI-enabled agriculture. And this is something I'm going to probably raise more questions, which is what we do in the first part of our institute growth, right? Is identify important questions, start trying to address those, and then think about how we move forward and kind of grow in the field of AI-enabled agriculture. So I'm the cluster lead within the AI Institute for Food Systems for agricultural production. And I'm also a professor at UC Davis, as we've mentioned earlier. So today, next slide, please, Steve. I'm gonna think a bit more about these 4 different areas. And I've got them separated right now into agriculture, artificial intelligence, sustainability, and equity. And I think there's an important question of where is the overlap between these different areas. So when we start thinking about bringing them together and identifying the overlap, it's not traditionally in agriculture. I don't think technology is usually late adoption compared to other types of industries. So we know that agriculture is actually one of the least digitized industries, according to a number of studies out there. So how do we address this question? Why is that? What role is there for artificial intelligence or AI? And I think Danielle and Elias did a great job of kind of demystifying some of this, and I'll do a little bit more of that in the context of agriculture as well. But what we really want to know is where's there the most potential for impact along these various axes. And so the institute that we have formed, AIFS, I think is really rich in breadth and depth, and I'm really excited to be part of it. So next slide, Steve. First, I want to start by talking about what is AI-enabled agriculture. So I think of this, there's a number of different ways you can break this down. One way that I think of it in the context of agriculture is with 3 Ps: perceive, predict, and perform. Okay, so the perceive side has to do with measurement or sensing. So here we have, this is how we generate data, right? So I put a few pictures. The top one is, that's a satellite that's equipped with a number of sensors that's flying around our planet, potentially numerous times a day, capturing various types of images, whether it has to do with thermal imagery, it might have to do with just standard imagery we're used to seeing, RGB, red, green, blue imagery, and other types that can potentially tell us something about the state of agricultural production at any point in time throughout the growing season. We've got other ways of sensing or perceiving agricultural environments that can be on mechanical types of devices, whether that be as harvesters. In the case of the bottom left, that's a harvester harvesting grapes. You can equip those with sensors. quickly generate massive amounts of data, or we can have other types of devices that are out, such as the one on the bottom right, detecting water use, for example, in a field. So all of this perception side or sensing side generates potentially a lot of data. So what do we do with that data? So next we have to use it in some way that can be actionable, or we can take actions on, right? And so that for that purpose, we need to convert that raw data into actionable information. And so this part is the prediction portion. So here we might want to know how many grapes or how many almonds are there in the field at this point in time, so we can project yield. How stressed are our plants, so we can precisely irrigate, so we can potentially lead to more sustainable water consumption. How do we apply nutrients through fertilization? We need to be able to link this measured side to the prediction side. And once we have the predictions, then we need to do something, right? So this is where we say perform. This is the action part. And that action, I'm going to talk more about momentarily, but it could be as simple as decision support, which means providing information to managers or decision makers so that they can decide how to manage more precisely, efficiently, sustainably, and equitably in their particular location. Or it could be all the way on the other extreme, driving more autonomous types of management activities through either robotics or machines. Okay, so the next slide, please. So first I want to address this issue, which I think we've each got a different perspective on, which is what is driving the AI hype? So I'm sure it's hard to distinguish what all the way on the one end that Danielle mentioned about the machines taking over the world from the other end of what is actually happening. And so I want to talk about a bit more of that. Next slide, please, Steve. Thanks. So here, this is what in my mind has really, like, in the last 10 years, we've actually had a pretty big change, a step change in what the amount of data that machines can consume and the amount of effectively predictions that they can generate and the accuracy and performance of those predictions. So what is actually driving that? So first we have lots of data. So the first trick is, okay, I told you we're generating a lot of data. I'm showing you some different ways that's generated. Video, audio, other types of sensor information. It actually takes up a lot of space on your computer. Anytime you've downloaded a video, you'll probably know that you'll quickly clog your hard drive up. So imagine getting this all day from thousands of different sensors into one location. How do you, once we have that, these machines can actually use this information. How do we do that? Well, there's been the development of a lot of AI enabling software. So this is basically something we're thinking about being a teaching institution, is that it needs to be easy to use that data and do something important or impactful with it. And so people have developed libraries, and this is just a way of saying they've made it easier to write code to use that data and make it actionable. So that's the AI enabling software. And then the third piece is AI enabling hardware. And this might be the most important part of all this, is that we have been, in the last 10 years, there's been a lot of emphasis on developing hardware that can actually crunch through hundreds to thousands of times faster these massive data sets. Okay, thanks, Steve. So let's move to the next one. So who could AI-enabled agriculture impact? Well, there's potential impacts here for labor and farm workers, right? Because there's, as I'll talk about in a minute, there's a lot of manual labor involved in the production of the foods we eat. There's also potential impacts on farm managers and owners, where we have decisions that need to be made that will affect both labor and the environment and effects on human and ecosystem health. And then finally, there's society more broadly, where we have all of these agricultural production systems existing, and we are directly impacting and they are impacting us. So we have these number of different groups that could be potentially impacted by AI-enabled agriculture, but what could it impact? Next slide, please. So we've got resource consumption, right? So if we could make better predictions and drive better decisions, we could reduce our resource consumption. And that could be anything from fertilization inputs to water and irrigation inputs to pesticide, biocide types of inputs, and hopefully driving all those down to the minimal amount that is required to produce high quality, nutritious food. Next slide. We also have ecosystem health impacts potentially, which are going to be, in this case, I've got an image of eutrophication, which is the excess amounts of nutrients that end up in waterways that drive algal blooms. So you end up with, in this case, the potential for making big impacts for AI and ecosystem health. That's assuming we do it right. And I'll talk about that in a minute. Next Slide, please. And then finally, of course, we have climate change, which also we have a very complex system and a lot of variables which people are trying to track using these sensors. And how do you bring all of this together? And as Danielle mentioned, machine learning, what it is best at is bringing together lots of information and extracting complex patterns from that information. So climate change is a great example of that. So now, given that these potential impacts are there, what are the potential risks and rewards of AI-enabled agriculture? All right, so I wanted to bring up, this is kind of a little more on how humans, the equity and the human interaction side with AI-enabled agriculture. We've got this, what I call the human AI interaction spectrum. All right, so all the way from no interaction between human and AI. This is how a lot of agricultural processes are done now. This is, for example, we've got great, some sort of thinning or harvesting going on the left, which is done manually oftentimes. You've also got then some level of interaction, which I think there's a lot of growth in this area right now, which is related to collaboration. So how can we build systems that can make the process of working within a farm environment better from a human health perspective? So this is an example of an autonomous robot that is effectively, they call it autonomous wheelbarrow. So it's moving around and trying to show up at the right time so that it can be loaded and the fruit can be moved around, whereas otherwise it would be people carrying these or moving these in actual wheelbarrow types of devices, right? And then we've got autonomy, which is full autonomy means that we have a machine that is autonomously doing the action itself. So there's a lot of ways that humans and AI types of systems can interact. Next slide, Steve. And there's a lot of potential ways that we could think about how that interaction could find itself into the future of agricultural production systems. So you've got all the way from job displacement through job enhancement through job creation. And I don't think that we know the answer to how this is going to look, but we have the opportunity to shape how this type of outcome, the future of AI in agriculture, is going. And so that's part of what we're trying to think about at the AI Institute for Food Systems. And these are all important pieces. You know, the interaction with machines and AI, a lot of, I think one scenario is that you have some job displacement where there's manual labor that's being displaced potentially by machines. On the other hand, you have job enhancement, which is that a lot of this work, I drive a tractor for a lot of my research. I'm out there, that's the nice job too, right? That's in terms of physically, and it's hard. Like to do it for 6 to 8 hours straight is hard on my spine because underneath the seat is literally the only suspension that the tractor has, shaking you up and down the entire time. So there's potential, how can we use this for enhancing those jobs through this AI-enabled collaboration and job creation? Of course, there's a lot of new types of jobs that would come out of this. How do you where's the technician types of jobs that interface and manage these types of systems? Okay, next slide, please. So here I've just kind of described a little more detail of how these different potential interactions with labor, and I think there's a lot of issues potentially associated with equity that come up whenever you start talking about this. And I think maybe some of you heard our colleague Aaron Smith speak a few days ago from the ethics group, who are really thinking in depth about a lot of these issues and how we measure and try to understand and guide these types of questions. So next slide, please. On the resource consumption and environmental impact side, there's the opportunity for using AI-enabled agriculture for higher precision management. So higher efficiency agricultural production, where we get more out of what we're putting in from an inputs perspective, and more productivity, where we're generating more from any given piece of land potentially. Next slide. So here, this is how I think of the different opportunities, places where we're thinking about, we have some research projects going on. They focus on these different types of resource inputs. So you got it, when we're thinking of a site for a farm, we have all the naturally occurring or site-specific variables, such as what's in the soil already, nutrients that are in the soil, the irrigation, the rainfall, precipitation that's going to fall. There, you've got other types of light, various things that are affecting plant-based systems at least. And then you've got all the inputs that we put in as humans, and managers decide what to put in. So again, this is a complex system. It's hard to make predictions on what happens as you're changing all of these parts simultaneously. And this is where machine learning can really help us hone in on the important pieces of the signals in all of that noise. So can I see the next? Yep. from these inputs, we get some outputs, right? So these are the things we're interested, these are the things we really care about. I think growers really care about in terms of what we're trying to control or guide or increase the efficiency or productivity of, which is mass. All I mean is that is yield, right? The amount we're getting out per amount of land. Chemistry, things like flavor, aroma, nutrition, these are all qualitative aspects of foods that consumers care about and we care about as growers and producers. And then also cosmetics, which is how the food looks. And of course, we have different needs or for that, depending on who we are. And then so the food waste, finally, there's an opportunity here for really guiding missed fruit, missed foods, underripe, that's during the harvest. I mean, if you're going through and harvesting, you might miss some fraction of the total fruit that's out there and leave it hanging if it's mechanically done. Underripe, overripe, infected by different diseases. These are all drivers of the amount of food waste that ends up in our system, which we also would like to reduce. Yeah, so I think there's opportunity to minimize certain aspects of this and maximize others of these, and that's sort of what we're focusing on as a systems level. Just a couple more slides left, and so here we have the question. I'm trying to think about the question of what are these endpoints? We talked about performance, right? What are the things we're trying to do? Well, oftentimes growers are wanting to be able to predict what crops are going to be like in the future. Whether that means how much fruit am I going to have at the end of the season? How much nuts am I going to have at the end of the season? And to do this, we need to know about how the plant is, the health of the plant. And so we want to be able to make predictions related to water and nitrogen demand, maybe disease pressure, yield, and quality. And then there's also the question of what we call actuation, but all that means is doing something in the physical world, right? And that might be something like spraying on some sort of, very precisely spraying on some sort of weed control agent. Thinning, pruning, weeding. We don't want to blanket do any of these. This is where we're interested in the highest level of precision we can have so that we can really reduce it down to the minimal amount of inputs that we need to produce something really high quality and nutritious. Yeah. And then there's a couple issues here that I just wanted to raise because I think these are important questions. I'm not going to go into great detail, but they're related to, as we increasingly rely on AI-enabled systems, we're have questions about then security, safety, and reliability of those food production systems. And food production is obviously a critical component of our economy. And so how we design systems and checks in those systems that give us information and open up what many people think of as a black box of AI to the farmers and growers and stakeholders is important. And these have to do with issues of security, again, safety, and the reliability of the machines and/or systems that we're building. Deploying. And then the final slide. This is another issue I think that we should be asking a lot about, which is explainability and trustworthiness of the AI. And so this is, again, creating systems that give us useful information for making decisions about those AI systems. So this might be I have a sensor that's out in the field and it's going through and trying to tell me, oh, I think I see a diseased plant. And then I say, well, go cut that, pull the plant out of the ground and let's remove it and replace it. I don't think every grower is going to want to do that without knowing why are you recommending this? Why do you think this is diseased? What do you see? Because when someone goes out, say it's a specialist, an extension agent, or someone with knowledge of this goes out and looks at this and they make a recommendation, they give you information about why they're making that recommendation. And so building that sort of explainability into our AI systems and building trust with our AI systems is a critical aspect of what we're interested in understanding and defining early on as we're starting to grow these types of systems and put bounds around them. So that's all I've got for now, and I'm excited to have any sort of questions from you all. So thank you.
All right. Thank you, Mason. We are going to take a break now for about 5 minutes until 11:30 to allow the switchers to get our panel all viewed in front of you. So with that, we'll be joining you again at 11:30 as a panel. And please type any questions into your question area. Hello, everybody. We are back with our panel on AI in the food system and fair and equitable food system. What we're going to do is to take your questions and pose them to the panel. And first off, we have a question that came in that was, this is for Danielle. How do we use AI to make food more equitable?
Yeah, so I did not touch on that in my talk. It's less of my area of expertise, but I'm happy to talk about it. So first, I should probably introduce a concept of food deserts, and that's when people live in an area where they don't have access to fresh foods. And so that's like just fresh fruits and vegetables. We in California, there are about a million people live in a food desert. And so one goal is to be able to bring more fresh fruits and vegetables to people who live in those food deserts. And so AI is one tool that one might use to be collecting data on where people are, where they're shopping, whether they're getting the food that they need, and to be able to sort of speed up that loop of nutrition policy implementation, evaluation, being able to speed up that loop to be able to provide methods that work. Yeah, and then the second aspect to that is making food that's cheap enough that people of every income level can easily purchase those fresh fruits and vegetables, and that's more Mason's domain of how do we produce the food.
All right, Mason, over to you on that.
Sure. Yeah. So again, like Danielle said, this is not specifically my area of expertise, but I think we're learning a lot, and hopefully we'll grow in our knowledge of this. So in terms of the production side, I think that being able to be more precise and efficient with our production, like Danielle said, could, we hope will bring cost down, which should make access higher. I mean, that's from a very high level. I think there's a really good question, which I'll look forward to answering in a bit, about producer size. So how there's an equity question across technology access and availability, depending on the size of the farm and the operation that's happening, right? And so what you often see is, of course, when you have more capital you can spend on technology, you have access to it more quickly and earlier on in the technology's development. So that kind of gives an advantage. So I think there's this important question which someone had asked, and we'll talk about in a bit, of how you can transfer that type of development of AI-enabled technologies from larger growers to smaller growers. I think there's also the question of equity with respect to farm labor and workers' rights, which I think is an important question. How you can ensure that there is some level of equitable conditions under which those workers are working, and fair and equitable conditions. And so I think that's an important question about the interaction with and potential for machines, but one that needs to be sort of approached in robotics, one that needs to be approached cautiously but optimistically, I'm hopeful about, because I think there's a lot of room for collaboration. What I see as the most successful, and many of the technologies that are coming out now, are the ones that enable people to do part of the job and focus on the parts we're really good at, right? Maybe not bending over thousands of times, because that can be very quickly hard on our back, something along those lines. And so being able to make it more fair and equitable in that respect, I think is really important.
All righty, thank you. And I'm going to pass along a quick non-question, a compliment. That is, I don't have a question, but thanks for demystifying what AI is and how it and machine learning are used in this domain. Really clear, thanks. So thank you, panel, for that. Moving on, we have this. We'll start off with Danielle. It's how does the average person access this information to improve their health? And part two is I'm thinking of diabetes, obesity, like use an app to enter what you're eating, etc.
So, so the USDA, disseminates this kind of information through the dietary guidelines for Americans, but still, that's still a lot to read. So, a more useful app would be at myplate.gov. It's myplate.gov. There's a lot of information and resources that you can use, and there's even an app you can download to check your own diet. And as a researcher at the USDA, that's one of the things I work on is like what do those dietary guidelines need to be? And so that's what our research and development is developing the scientific evidence behind the dietary guidelines.
All right. Thank you very much. And then we'll move on to another question. What are some challenges you have found when dealing with farmers to become familiar or comfortable with utilizing AI in ag production? And Mason, we'll send that to you.
Sure. I think, like much of us, the average farmers they're pretty familiar with your technology, smartphone, et cetera, right? We're all kind of comfortable interacting with that types of technology. The question is, what we don't think about a lot is how frictionless the technology is to interact with. So that's one piece. So as any of you know, if you've used a piece of something you went and bought, a speaker, a smart speaker, or whatever it might be, something, and you try it and something goes wrong that you don't expect, the first time you kind of give it, you're like, maybe that won't happen again. And then it happens again, you're like, okay, I might throw this in the trash. And then like by the fourth time, some bug happens that you realize is happening. You think, okay, I'm done with this thing. So you get a pretty limited amount of time to build confidence in the capacity of any technology or tool. And I think part of that is building seemingly simple interfaces that are able to hone in and be used easily in the context of the user. So I think farmers want actionable information, and they want to know that what the information they're using and providing is going to give them predictions that are useful. So I think one of the biggest challenges is just showing that there's value, right? And I think that there does need to be value. If there's value there, then it's pretty apparent, but that's one of the big challenges is demonstrating end to end that here's the information, here's the sensor, here's how we make the predictions, and here's how you can use it right now to do something that has value to you.
All right, thank you. The next question will start off with Danielle, and it is, thank you for your study of healthy adults. Are there plans to survey adults with digestive diagnoses such as functional dyspepsia, GERD, IBS, etc.?
Great question. I actually would love to study people with various digestive diseases, but at the USDA, we're chartered with helping people prevent. What are the dietary guidelines to prevent those diseases, where it's more the NIH, National Institutes of Health's domain to study disease. So I do collaborate with people who are MDs and get their funding through NIH. And I would like to also add to this that we actually don't know completely what is a healthy microbiome. And that is another reason to study healthy people, is we need to know what is this goal that we're trying to get people who are unhealthy to. And it's certainly being free of symptoms, but there's a lot more to health than that. It's also not falling back into the symptomatic category. Something as simple as, is your microbiome resistant to a new pathogen? That's something that you wouldn't know without somebody being challenged by that pathogen. I hope this makes some sense about why we study healthy people, but yes, both healthy people and disease need to be studied.
All right, thank you. And the next question we'll send over to Mason. It's what are some challenges you have found when dealing with farmers to become familiar or comfortable with utilizing AI in ag production?
Yeah, I think this is somewhat related to the last question that we had about comfort and familiarity, but I do think that so here's an example. I think there's an interesting example here. If you can build a technology, let's say you go out and you show, I'm going to make a prediction of what your yield is going to be in a certain location. Okay, so let's say you're growing lettuce, and I want to go out and say, all right, 3 months from now, I'm going to tell you that this location right here, this little 10-foot by 10-foot patch is going to produce this many pounds of lettuce. And then what's the first thing you as a farmer are going to do? You're going to say, okay, we'll see, right? You'll wait and see, and you'll take that amount of lettuce and you'll go measure it and say, how well did it perform? And if I predicted 100 pounds, just as a random number, and it was 50, you're going to suddenly lose confidence in the prediction and the tool. And so the next time you want to go out and use it, you will probably be skeptical. You might test some more. You might say, I need to test this another 10 times. Or so I'll see how it works, and say it doesn't perform that well every time. And if all you can do then is just walk away from that tool and say, you have to make a choice. Am I going to use this? And you're probably going to say, no, I'm not going to use this. But there's an alternative, which is that you can give feedback to the tool, right? And so if you can give feedback to the tool and see that the next time you're like, what did I do wrong? Here was my prediction. You're like, you were terrible. Okay, thank you for letting me know I'm terrible as a machine. What did I do wrong? And you're like, look, you were predicted under every single time. Here was the actual values. And here's some of the ones you said there was going to be large lettuce heads here and there weren't. So let me correct where those are at for you. And you can feed that information back into the tool. And next year you go out, or the next round, if it's producing cyclically, and then now you're predicting 80 pounds and it's 100, and you move closer, you start building trust with that tool that you're making predictions with. And by enabling an interaction and kind of an interface to provide feedback, you see that it is learning from what you're teaching it, right? So developing some sort of relationship between models and people, predictive models and people, enables this sort of, I think, adoption potential. And so that's one of the things that I'm trying to think a lot about.
All right. Thank you, Mason. We're going to go now to a question that I believe I'm going to send to Danielle first, but Mason may want to add into, and that is, how do we use AI to make feeding the world more sustainable?
Okay. So I think I'd like to answer this question with a particular example, because it's easy to play, buzzword bingo, but I'll give an example in the dairy industry, and this was actually implemented by Arla Foods, where they developed a tool to predict how much milk was going to be produced at each farm, so that they knew how many trucks to send out to the farms and at what times. And so this dramatically reduced costs, and it reduced emissions. So all those feed into sustainability. So I'd say it's sort of as an overarching answer to how does AI help sustainability, it just helps us optimize for so many different variables in a way that a single human can't, that it makes things more efficient.
All right, thank you. Mason?
I'm going to follow Danielle's example. Danielle's lead and give an example too, since we talked pretty broadly earlier about some of these questions, sustainability. So in terms of environment, and in California, we know that water is a massive issue. And water availability is pretty scarce and increasingly scarce. So how do we manage more sustainably in terms of our water inputs? Going back to the idea of the 3 Ps that I mentioned of perceive, predict, perform, you can break this problem up in that way, right? So you can say, okay, first we need a way of saying, let's go out, and people are trying to do this, right? There are companies trying to do this, researchers trying to do this, where we go out and we equip a field with sensors to say, what is the water status? When you go out into a large field of almonds, for example, you may have a lot of variability in how much water is available, even based on the soil type that's there. And if you don't know that there's this variability in the soil, you might just blanket apply the same amount of water to every single almond plant. But instead, if we can develop lower cost sensors that we can then apply across the field at kind of a lot of them in higher resolution, you can then have information on which plants are more likely to need more water. So you're perceiving and making the predictions. We have to build models to say, let's use that information and predict how much water they actually need. It's where some targeted studies might come in. And then you say, now performs is the action portion. So we need to go in and water those plants accordingly. So then we need ways to feed that information back about different needs at higher spatial resolution, or higher, within the field, to individual plants. So we might have a system that can trigger watering at smaller locations within the broader field. And by doing that, we'll see, you might see 10, 20% reductions in water use over the course of the season, and multiply that times all the almond producers in California and different crops. Then you can really start seeing an impact on total water use.
All right, thank you, Mason. This is for Danielle. Do you envision a day when I will take a snapshot of my food plate and get immediate feedback on how eating it will affect my personal gut health?
I would love that, and that's one of the things I work towards. It would be great to be able to take a photo of your meal and get even some really simple red light, green light, yellow light feedback on whether that's okay to eat. I'll say a few things about that though. First, like, you would need to know a starting microbiome, have your microbiome analyzed, and so that you'd have like that initial condition. Another caveat is that our microbiomes are always changing, so that one snapshot may not reflect where you are, a month or even a few days later. So that's sort of the holy grail, but I'm also realistic. It may well be that most healthy people can eat most things. It may just be totally fine, and that red light, green light, yellow light system might really be for somebody with IBS or some condition where there really are foods that they need to limit. Another caveat is that it's a single meal may not matter. It's what you're eating in aggregate, so it wouldn't be just that one plate of food, but it would be, tracking your history, many pictures over time. And, if that's the 10th time you ate a brownie that week, you'd get the red light. But that's a more obvious example. You won't need an app to tell you that. And the other realistic caveat is, 20 years ago, I can remember going to a conference where they were talking about nutrigenomics and like being able to sequence our genomes will know everything about what people need to eat. And it turns out that there really are, yes, there are some genetic variants that should impact what you eat, but very few of them, not nearly as many as we expected. So I expect the microbiome to go through a similar level of reaching hype and then realistic. So yes, there will be some relationships between diet and health, but it won't be as the magnitude that people necessarily think that it will be. But definitely we should work towards that goal, because it will be helpful for some people.
All right, thank you. And we'll start this next question off with Mason. I believe both of you may want to address it. What are the risks or unintended consequences of using AI in food systems, and how can we mitigate them?
I think that's a really good question. And I think it's one we need to, that involves probably a conversation with a lot of stakeholders. So I'll try to do my best to just highlight a couple, but I'm sure there are many potential more risks associated with it. So I think that one of the things I mentioned earlier is that if you build a system, so AI systems, and when we say AI systems, we're really usually talking about some combination of like hardware, whether that's robotics or something else, maybe, or just information systems, which is more of a modeling approach, right? So the modeling piece, which is the machine learning or deep learning that Danielle talked about, it's a statistical program, right? So it's data driven, which means that you're giving it lots of data and you're telling it usually what you're looking for. So you've got like an input, which is all this data, and then output, which might be something like, I don't know, I keep using the yield example or water use or something like that. And you say, help me find the relationship between these inputs and this output. And you've got this box in the middle, which is your machine learning model. And so it's looking for relationships, and it will find all sorts of relationships. There's an interesting classic example of this, so there are these fish, there's a competition. So they hold a lot of competitions in the machine learning world. And they say, all right, we've went out and all these people took a bunch of pictures of different types of species of fish in this lake within part of somewhere in Central Africa. And they said, can you go in and we need you to help us build a model that learns to classify, meaning just tell us what species of fish these 75 different fish are based on a small photo. So they went out and they put this competition out there, people competed, and someone won. And they did a great job. And they said, wow, can you tell us how you won? And so the way that they ended up winning, they said, well, our model, when they went in, they said, we looked at it and it turns out our model was seeing the date and the timestamp on the bottom. It learned to predict the timestamp at the bottom of the photo, and they were taken in different locations at different times. So all the fish from one species had been taken with one camera at one time, and the model learned to just read that. It learned to read that little timestamp in the bottom. And so if you don't have a way to open up the models and give feedback to those people that are using it and have a dialogue between the model and the people, you run a risk of not knowing why the model is making predictions. And as soon as you go to outside what's called extrapolation, you go outside of your training data set, you're in the Wild West, right? So like you might end up just out somewhere predicting for a reason that doesn't make sense. And it's gonna make it useless predictions. And so I think that's one of the big risks, is not understanding our models. And so making sure that we do that is really critical and important piece.
All right, thank you, Mason. Danielle, any ideas on that?
Yeah, I think the unintended consequences is just that our planet is a really massive system that you can't possibly model everything. And so, you know, to give you an example about how it could go wrong would be like, say people are using their nutrition apps and the apps are telling most people, oh, eat more fish. And people all go and eat more fish, and then we deplete the fish supply, you know. So there will always be that sort of thing happening. It's sort of like probably a lot of people have used Google Maps, and you're driving, you know, your Google Maps is telling you to drive a different way so that you get around, you know, the car wreck or whatever. But then everybody takes that path, and there's a bottleneck. So that sort of thing is going to be inevitable with this kind of technology. But I don't know about you, I would not want to go back to the time of not having, you know, navigation and old school paper maps. So yes, there is a big advance, but with every big advance, there's some caveats.
All right, thank you. We are nearing the end of the session, and I wanted to just pass it to our panelists one final round and just ask you, are there any takeaways that you'd like our audience to take away from the discussion today? And we'll start with Danielle, you first. Okay.
I guess what I'd like to say is I know a lot of times people fear technology, especially things that they don't understand, and there can be, you know, downsides to any technology, but and you know, we've all experienced that thing of, you know, you're looking at your phone and you get advertisements for stuff. Like AI is in use today, and it's in use to like target us to buy more things, but in the, you know, hands of those of us who work for public good, these tools can really improve our lives, and that is, you know, for getting more sustainable, nutritious food accessible to more people. Thank you for listening today.
All right, Mason.
Yeah, I think I just want to reiterate some of the things Danielle said earlier about AI not being a magic wand, but it can be very powerful. So with that power, we probably just need to ask lots of questions and do it early on and have conversations about where we see the biggest opportunities and risks in deploying that technology out in agricultural and food systems more generally. So please engage with us. We're here. We've got a whole broader outreach and education, community engagement piece of our institute, and I think we're excited to interact with growers all the way from small to large, and people who are eating food, which is pretty much everyone. So thanks for having us. All right.
Thank you very much to our panelists, and anybody that wants to follow us, we are on LinkedIn, Twitter, and you can catch our website at aifs.ucdavis.edu. With that, we thank our panel, and we thank all of our audience as well. Goodbye.